Good evening. This is an explicative video evaluation of the first partial exam of computerized control. In this video, I will explain in detail the importance of the method root locus in the discrete time systems. So yeah, let's continue. Why root locus? The root locus can be described as a control system design technique, that is, control system design and analysis. Two questions can be answered with the application of this technique. One regarding the design of the control system, and the other one the effect of variation on a control system already designed. To gain a good understanding of the root locus, the person should know what role the zeros and the poles of a transfer function play in this method. The first thing to have in mind is how they behave in the respective S or seed plane according to the location or to the amount of them in the plane. The root locus method allows us to move the roots in the S and seed plane, and watching how this affects the system in addition of the poles and zeros takes place only in the feedback controller, not in the plant. You cannot, you should not add or subtract zeros and poles from the plant, just the feedback controller. That must be clear. So the node that I have right here, it's pretty similar to the one that the teacher showed us in the class of root locus. I wanted to put it here because it explains very well the terms of stability in both planes. We have here how to get the poles, which both ways are practically the same. And we have that for the S plane, the poles must not go to the right-hand side of the plane, just to the left-hand side to maintain stability. And here on the C domain, we have the unitary circle, and they cannot get out of this unitary circle if you want to achieve stability on your system. Here we have a few formulas and a few examples of the poles in the S-plane. For terms of summarizing this video, I will just say that this one right here is for the phase of the poles, which the examples are right here. When they collide, they go to 90 degrees. When they are alone, they go to infinity to 180 degrees. Here we calculate them with the formula. This formula is for the centroid for the collision point. So yeah, this is pretty much everything I want to show in this diapositive. So to continue, we have the theory behind. Oh, I don't know why it stopped. So, well, the theory behind this, before subtracting or adding poles and zeros, it's important to know how the poles and zeros affect the system according to their position. This is very important. So we have the relationship between the S and seed plane is expressed as this. Here we have the pole. Here we have the sampling period. And we can divide them in these two to get the distance to the origin from the pole and the phase. So in this way, we can convert the poles to the S from the S plane to the seed plane. Here are a few examples of that we should have in mind when the pole reaches -1. We are talking about the Nyquist frequency. When the pole is the further away the pole is from the unit circle, it grows. It keeps growing. We have here oscillation velocity that is determined by the phase of the poles. And yeah, here we have so I'm trying to do this fast. Here we have the undamping, because it is on the border of the unitary circle. If it were to be more inside, it will have a little bit more of damping. Here we have the slow pole because it's close to +1. So yeah, and this is how the poles behave. These are a few examples and circumstances of behavior of the poles in the S plane, in the Z plane, sorry. So to continue, we have the example. I'm going to explain this real quick. So we have the controller, the gain here that we will control to reach the stability that we want for the system. And here we have the HC transfer function of the plant. We have the transfer function of the feedback controller. We have the equations are in the S domain, as you can see. This is because we are going to apply the zero order hole to get them to the discrete time domain, to make it a discrete time system function, sorry, a discrete transfer function in discrete time system, sorry. So we have here the samples that we are going to be using. I hope that I will be able to sample the three of them, but I don't know if I will have the time. So we are going to open MATLAB right now. So here in MATLAB I have, sorry, this is not. Here in MATLAB I have everything already coded, because if not, well, I will last long. So here we have we are declaring the S to make the continuous time transfer function. We have GH that represents GS in the diapositive I just showed you. We have here the transfer function of the plant. We have the transfer function of the feedback controller. We multiply them in order to apply this is right here, both multiplied. And in order to apply this function, the continuous to discrete function, applying the zero order Hall method to get a discrete time transfer function. Sorry. We use first of all the sample time of 0.5. Here we have the transfer function in terms of set, and I used CISO tool to show the behavior of these poles on the root locus editor. So we have to erase this. This is not useful right now. So here we have the root locus editor. We can see where the poles and the zeros are, how they behave, how they meet each other. None goes to infinity. So I'm gonna try to zoom this a little bit. Okay. Here we have the step response from R to Y, which means from input to output. And as we can see, well, we have a certain time of approximately 30 seconds, which is not very good. But let's see what happens if we add a real pole to this system. Let's see inside the same unitary circle, but let's say over here close to the Nyquist frequency. So what happens is that, as you can see, the oscillations become have more velocity. The oscillations have more velocity. The settling time is practically the same. If we remove this, the rising time also changes. The overshoot changes as well. So let's erase this pole, and we have back the step response of our transfer function from of our closed loop controller. So yes, this is pretty much everything I wanted to explain in this video. Let's see what happens if I add a zero over here. Sorry, that's the 8-minute limit time. So as we can see, adding a zero right here, you can see that this pole meets the zero right here, and it makes the it makes the settling time a lot shorter. It makes the overshooting a lot shorter, and as we can see, we can appreciate. Sorry, I thought I was pointing. We can appreciate how it is more stabilized than before. So yeah, and I can keep playing with this, but I have no more time to keep explaining myself. So I think that I have made myself clear in the application of the root locus method and how it has big impacts on the behavior of the system, step response, frequency response, impulse response, I'm sorry. And it has a very, very unique meaning in the stability of the systems. Let me see if I can show you quickly what happens if I drag them farther away from each other. We can see how the oscillations increase and how the amplitude of them increases a lot. And if I take them back to their original place, well, sorry, that was too much. We have what we had before, technically, and sorry, it's a little bit slow, but yeah, to not make this any longer. Thank you for watching, and I hope you like it, teacher.